We are off and being recorded. So we can start.
Well, hello, good afternoon, everybody. Always nice to meet you in a different context. And today, what I want to talk about is the fact that even though we like to keep them separate in our minds, and we like to think of digital electronics one side and analog electronics on the other side, really and truly, that is only a convenience because in real life, we need to consider all aspects of analog signaling when we working with digital systems. So, what I'm hoping to convey to you here today is why it's important to understand the analog behavior, even though we're dealing with digital signals, which presumably have nothing to do with it, and some of the key things you need to look out for when you try to connect these types of signals together. So, I want to start with a conversation about what is an analog signal. A lot of people say to me, well, Miss, what do you mean when you say an analog signal? Do you just mean something that has, infinitesimally small values? What do we mean by an analog signal? So for the purposes of today, we're just going to talk about voltage signals. We're just going to talk about voltage signals. And when I talk about an analog voltage signal, what I mean is that the signal is continuously varying over time with no restrictions on the precision of the signal. So, for example, we know that we could have a time variant signal. It could be a pure signal, or we could somehow have superimposed that behavior on another signal. So, for example, AM signals or FM signals, where AM stands for amplitude modulation. The signal that we are interested in is actually the amplitude of the voltage signal. So, we're looking at how the envelope changes, and that's the information we're interested in. So it's a voltage signal, but what we're interested in is not the actual level of the voltage at each point in time. We're interested in the amplitude envelope in an AM signal. And similarly, for an FM signal, what we're interested in is how the frequency changes over time. So that's a frequency modulated signal. So all of these are analog signals, whether it's the pure signal or the amplitude modulated signal or the frequency modulated signal. Any one of these, we're trying to get some information across, and we're doing that using a voltage signal that is continuously varying over time with no precision restrictions. So that's what I mean when I say an analog signal. By a digital signal, what I mean is that there's a voltage signal, again, continuously varying over time. But in this case, I'm interpreting this signal to represent one of two states. In this case, I'm interpreting this signal to represent one of two states for a particular point or interval in time. So the commonest form of this is we know we represent voltage signals and we look at the level. So we say, well, when the voltage is high or positive, we'll interpret that as a digital 1. And when the voltage signal is low or ground, we're going to interpret that as a digital 0. But really and truly, there's no constraint on what the nature of the digital signal is. We could have an inverted digital signal. We could have a digital signal where we use plus and minus voltages for the 1 and 0. We could even have a digital signal, as in Manchester coding, which we have an image here at the bottom, where what we're interested in is the transition in the middle of the bit period. So you'll notice that the transition from high to low is what we code a 1 as, and the transition from low to high is what we code a 0 as. How we choose to code our two states is up to us. There are many, many, many different ways that you could code two states onto a voltage signal. But the key here is that the information we're trying to transmit, we are coding it as a signal that encodes two states at any point in time. So do I have any questions at this point about the difference between a digital and an analog signal? If we do, just use the icon to raise your hand. If not, I will keep going. Okay, great. So given that we have analog signals and we have digital signals, and philosophically the two are very different, why are we trying to mix matters? And there are three key areas for why we want to mix matters with digital signals and analog signals. The first reason is because under the hood, digital signals are analog signals. There's no getting around it. And if we're not careful, if we don't pay attention to the analog constraints, we might break the digital circuit or the digital signal. So because under the hood it is analog, sometimes we have to look under the hood and make sure that we're not causing problems. The second reason why we need to pay attention to this is because sometimes we actually want to use digital methods to process an analog signal. So maybe we want to decode or extract information from my voltage signal using some digital techniques. I am sure Dr. Mudin, if not in this course, at some other point in time, will talk to you about various techniques to extract frequency information from a signal. So maybe I want to process that information using a digital system. In order to do that, I'm going to have to convert my information from analog to digital so that I could work with it. And similarly, if my goal is to generate an analog signal, I might have to convert a digital signal to an analog signal at the end of the process. So sometimes the issue is that I want to convert in and out. And last but not least, it could be that we're trying to improve our ability to transmit the signal. It could be that we're trying to improve our ability to transmit the signal. So in this case, we would be talking about things like digitally encoding the analog signal to make it more robust to noise over long transmission distances. And we could talk about things like pulse code modulation and other encoding techniques for analog signals that you want to transmit over long distances. Or maybe you want to store in files. So these are techniques that you would find that, when we talk about digital audio files, what have we done? We've taken an analog audio signal and we've encoded it so it could be stored digitally. So these are the three key areas. I want you to remember those as we go through these slides. Go ahead, Sadie. I see your hand.
Yes, miss. From the previous question with the digital signal, when you say interpreted as one of two states at specific points, you're talking about 0 and 1.
It could be 0 and 1. I'm being deliberately two states because we write 0 and 1, but it isn't always 0 and 1. Sometimes it's high and low, sometimes it's on and off, depends on the application. But it's two states. Yeah?
Thank you.
No problem. Thank you for that question. Any other questions before I move to the next slide?
Not from me.
Not from you. Okay, no problem. Okay, so under the hood, we want to look under the hood and make sure we're not accidentally breaking anything, right? So back in year one, you would have learned about digital devices and you would have learned about different logic families and what it takes when you create a digital device in a particular logic family to connect it to something from another logic family, okay? And in those situations, back in year one, most of the time, the devices you're working with have defined inputs and defined outputs. So some pins are inputs and some pins are outputs. If we're talking about a NAND gate, the NAND gate input is always an input and the NAND gate output is always an output. It doesn't suddenly change midway through life, okay? And we would have learned at that time that if you want to connect two devices so that they can transfer logical information between each other, if you want to connect two devices so that they can transfer logical information between each other, then you need to check three things. You need to check to make sure they have the same supply voltage and reference voltage so that you don't accidentally blow anything. You need to check that the device that is driving the signal or outputting the signal is outputting a voltage that does not lie in the indeterminate region for the device that is receiving. And finally, you have to make sure that the output can sink or source enough current for the other side to read the signal. So these three things have nothing to do with digital, but these are the analog constraints we have to satisfy if we want to be sure that the digital signal is received correctly. If you've heard of these three constraints in your year one course, give me a big smile. If you've heard of one or two of these constraints, give me a thumbs up. If you never heard of any of these three things before, give me a thumbs down. So if you've heard of all three of these before, big smile. If you've heard of one or two of these before, give me a thumbs up. If you have never heard of any of these things before, give me a thumbs down. Okay, I see I have about 16 responses so far. I'm looking for at least another 10. Okay, so based on what we see in here, it would seem that most people have heard of a couple of these constraints before. Okay, so these are the three constraints you need to make sure. This is the analog behavior underneath that is going to make your digital device work correctly or incorrectly, as the case may be. So for example, if I have a TTL gate driving an output that is being input CMOS, I think it's an inverter here, I would have to check and make sure that my V output low from the TTL gate falls within the region that is appropriate for an input low on the CMOS. And in this case, we're good because we could see that the region for outputting from the TTL gate, it goes up to 0.5 volts. So that's outputting a low. And that falls within the acceptable limits for the CMOS gate, input low. So life is good on that front. We can see in the circuit that they're connected to the same supply and reference voltages. So we're good on that front as well. And last but not least, we want to make sure that the TTL gate could drive enough current, whether that is sinking or sourcing, for the input. And we realize that the leakage current for this inverter is 1 microamp, and my TTL gate can sink or source up to 5 milliamps. So all is well when we look at this circuit. It's fine if I want to transmit a low from the TTL gate to the CMOS gate. Let's look at the corresponding case if I want to transmit a high. Let's look at the corresponding case if I want to transmit a high. Now in this case, the output high voltage for the TTL gate is going to be a minimum of 2.7 volts. So in other words, when I'm outputting a high, my voltage will be anywhere between 2.7 volts and 5 volts. And clearly that leads us to some uncertainty because we could see that 2.7 volts falls into the indeterminate region for my CMOS input. The CMOS input will only read it as high if it is over 3.5 volts. So this would be an example of a case where I'm only meeting 2 of my 3 constraints. And if I were to use this circuit, what would happen is that every now and again, my poor CMOS inverter would not be able to figure out if I was sending a high or a low. Even though I'm outputting a valid TTL high, the CMOS inverter wouldn't be able to read it as a high. So what do we do in those circumstances? So there are lots of different things you could do. One quick way to resolve an issue where you're having a problem on a single side of a logic level is to use a pull-up resistor in this case because we're trying to fix the high out. And what that pull-up resistor will do is that it will force, for want of a better word, the TTL gate to output a higher voltage. So very often you will see pull-up and pull-down resistors used in digital circuits. And the reason for them is we're trying to fix a problem that is a result of the analog under the hood. It might be a level issue, as we described here. It might also be an issue with an edge, because if you're coding using edges, rising edges and falling edges, the issue might be that your edge is not sharp enough and you need to sharpen it. So you would use a pull-up or pull-down to sharpen the edge. Could be you're also having some issues with slew rate. In other words, the signal is changing fast and you're not responding fast enough so that the CMOS inverter doesn't have time to see the high before it goes low again. Whatever the cause, you're going to see pull up and pull down resistors. And what we're trying to fix when we use those is some analog issues, which we would prefer not to think about when we're dealing with digital circuits. Now, in those examples there, I was dealing with some logic gates. In those examples there, I was dealing with some logic gates. And the good news with logic gates is that the inputs to the logic gates are always inputs, and the outputs of the logic gates are always outputs. However, to be confusing, when we come to microcontrollers, we have these things called tri-state buffers, and we introduce this concept of tri-state logic. If you've heard of tri-state buffers or tri-state logic before, give me a scared face. If you've heard of tri-state logic or tri-state buffers before, give me a scared face. Waiting in the chat, looking for at least 20 responses. If you've never heard of tri-state logic or a tri-state buffer, give me a thumbs down. So if you've heard of them, scared face. Never heard of them at all, thumbs down. Looking for at least 20 responses. Okay, so it would seem that most of the class has never heard of this thing. And of course, when we know Miss just going crazy, we were just talking about digital logic with 2 states. And Sadie clarified it for me, 2 states. We're coming with this tri-state logic now. So the reason for this is because on a microcontroller, you need to have the flexibility to change a digital pin from an input to an output. You don't need this flexibility on a logic gate. The inputs are always inputs and the outputs are always outputs. However, on a microcontroller, where we have what we call general purpose input-output pins, general purpose input-output pins, we want the flexibility to be able to change that pin from an input to an output, depending on what we're doing or what we need to do. So for use on microcontrollers, we use what we call a tri-state buffer and tri-state logic. So a tri-state buffer in essence is a switch. A tri-state buffer in essence is a switch that is controlled by one of the inputs. Let me see if I could draw a box here so I could highlight where I'm looking. So you see the switch here? So in the context of this discussion, B is the signal that controls whether the switch is open or closed. It's not actually a switch, it's actually a transistor circuit with some flip-flops. But for the purposes of this conversation, it's a switch. So B is the signal that controls whether the switch is open or closed. B is the signal that controls whether the switch is open or closed. So when the switch is closed, then the output signal is equivalent to the input signal. In other words, if I was outputting a logic high, I will get logic high. If I was outputting a logic low, I will get logic low. When the switch is open, then no signal can be output. And we refer to that as the high Z or high impedance state. When the switch is open, no signal is being output, and we refer to that as the high Z or high impedance state. In that state, we could use that same pin on C to receive a signal from the external world, and the signal A would not interfere with it. So when we talk about a tri-state buffer, what we're talking about is the fact that we could configure this buffer in 3 ways. 1, we could set it out to output a low. 2, we could set it to output a high. And 3, we could set it to float or go to the high impedance state. And at that point, the external world can impose a signal on the microcontroller. So sometimes people get confused with the tri-state logic. Not to get too confused, you could just think of the signal B as controlling whether or not the internal signals are connected to the external world. Now, I'm surprised you haven't heard of tri-state logic because everybody is using an FPGA board, right? If you're using an FPGA board this semester in another course, give me a thumbs up. If you're using an FPGA board this semester in another course, give me a thumbs up. Okay. And at some point in that course, you're going to want to drive signals from your FPGA circuitry out to some devices. At some point during that course, you're going to want to drive signals from that FPGA circuitry out to the real world. Can you give me some examples of the things in the real world that you might want to drive signals out to or receive signals from on that FPGA board? Looking in the chat for some examples of some signals you might want to drive things out to or receive signals from. I know we had a lab this week, so I'm assuming that you did drive some signals in some direction. Last week, sorry, I think was lab. Did anybody use any to display? Very good, Jamar. So signals left the FPGA, went to a display. PWM signal went to a motor. Excellent, Sachin. So you get the point. You have been driving signals in and out of that FPGA board. And in doing so, didn't you have to configure some pins as port pins and configure them as input or output in your VHDL code? If you remember that, yes, I had to set something up in some VHDL code to set it as input or output. I got 3 yeses. Okay, great. So what you actually were using there was tri-state logic. I'll leave you to go and check your FPGA board manuals, etc. to see, but that's what's going on. There's some circuitry that allows you to set it as an input or an output. I think it's called the port circuitry. And that's how it works. When you want it to be an input, you literally disconnect it so that you could receive signals from the outside world, maybe from a switch or a button. And if you want it to be an output to output to a display or to output to a motor, then you configure it as an output. All right. So when you have this tri-state logic, you want to be careful because the same problems that occurred with the connecting the CMOS gate to the TTL gate to the CMOS gate, those same problems could happen when you're working with a tri-state logic circuit. In fact, now you have to protect both ways because you're not quite sure what state the microcontroller is in at any time. So a lot of people will say to me, they're like, well, miss, it's not a problem. I want to connect a switch to an input. I'll just connect it straight because the input is high impedance. It's not going to need a lot of current. So I don't have to worry about anything. Once I push the switch and it's an input, all is well. And I have to remind them that the problem we have is that it's not actually a fixed input like on a logic gate. It's not actually a fixed input like on a logic gate. It's actually this tri-state logic business. And what that means is that somebody could accidentally in their code, VHDL or otherwise, misconfigure the pin. And if they misconfigure the pin, in other words, I wanted it to be an input, but I accidentally made it an output, or vice versa, then you could end up in a nasty situation where you press a button or flip a switch and cause your circuitry to short out. Now, causing circuitry to short out lets the smoke out. And I am told that the smoke is the magic component to any electronic circuit. You don't want to let the smoke out. The smoke has to stay inside the circuitry if you want it to work. Letting the smoke out is not a good idea. So you must always consider what protective circuitry you need to use to ensure that when you connect something to your tri-state logic pin, you protect both the device that you are connecting and the microcontroller. Is that a question you have there, Gianluca? No problem. Okay, so you'll notice in this configuration here, instead of just connecting the switch SW2 to my port pin, whether it's in or out, and then connecting the other side directly to ground or directly to my supply voltage, I actually have a resistor either side. So even if this was misconfigured as an output, I'll be safe, because if I'm outputting a low and the switch is open, then I'm not going to short 5 volts to the low that I'm outputting, because I have a resistance of 10 kilo ohms that will limit my current and keep things under control. Similarly, if I'm outputting a low and I switch the switch closed, not a problem. Current will flow to ground because my output is ground. Not a problem. So it's all good once I protect on both sides with resistors. So the key here is to remember that you have to protect. So even though it's digital and we'll be looking to drive a high or a low out, you have to remember that you want to protect. Same thing if you're driving a load. My apologies, there's no diagram here. Same thing if you're driving a load. So you might have your in or your out, and the signal's coming out. If I want to drive a load, that's fine, but I have to pay attention. I have to pay attention. What is the nature of my load? How much current does it need? If my load pulls too much current, what will happen to my microcontroller that's connected to it? So I might need to be careful. I might need to stage the circuitry so that maybe I get the microcontroller to switch a transistor, the transistor switches a relay, and then the relay switches the load. I might not be able to connect directly from one to the other. I'm going to have to think about the analog behavior of my circuitry before I connect a load to my microcontroller. Does anybody have any questions about tri-state logic and the fact that you need to pay attention? You can't just connect things. And I would encourage everyone to go and relook at the electrical characteristics for your FPGA board and see what circuitry they have built in there to protect both the FPGA circuits and the external circuits in case of misconfiguration. Okay, so we said the first reason that we're interested in talking about these things is because if we don't pay attention to things that are under the hood, we get problems with our digital behavior. So we want it to behave correctly digitally, and that way, the only way we get correct digital behavior is by paying attention to what's under the hood. The second reason we talked about is the fact that maybe I actually want to process some signals digitally. So either the signal is analog and I want to get it in so I could process it digitally, or the signal is digital and I want to send it out to an analog system. So in order to interface between digital and analog systems, you're going to need to use some signal conditioning circuitry. And we're going to talk about two classic examples of signal conditioning circuitry here today. These are the ones that you're going to come across most commonly. The first is a zero-order hold. I'm not sure if you've already looked at a zero-order hold in signals and systems. If you've heard about zero-order holds before, give me a happy face. If you have never heard about zero-order holds, give me a sad face. You've heard about a zero-order hold before? Yeah, happy face.
No, they wouldn't have heard about it as yet, but the idea about sampling, we spoke about that early on in signals and systems, and with a simple sample on hold, with a capacitor and a switch to go from the left figure to the right.
To the right figure.
We did do that already early on.
Early on. Okay. So everybody go back in your signals and system notes, because this is the real life example of what Dr. Mudin was talking about in that class, right?
When we were talking about sampling.
When you're talking about sampling, right? So you're sampling a signal, the gray line my apologies. The gray line here that I am trying to follow most badly is my analog signal. Now, part of the problem with converting an analog signal to a digital signal is that the conversion circuitry is slow relative to how fast the signal is changing. So what that means is that we have to sample it at specific intervals and then hold that value for the interval. So what I actually want to input to my digital system is not a continuously varying signal. I'm actually going to sample it at specific points in time and hold it constant for that time. So we refer to this as a zero order hold, basically because we hold the value constant. So you'll notice that instead of having a signal that varies up and down, it's now varying in steps. The circuitry we typically use for this is a pair of buffers with a sampling switch and a capacitor, as Dr. Medine said. The sampling switch is typically some form of transistor that you're using to switch between. So it's two buffers, a sampling switch, probably a transistor, and a capacitor that is going to be used to hold the voltage during the conversion. So the zero order hold is a very important part of the circuitry that you need for signal conversion. Now, depending on the circuits that you are using, some of them have the zero order hold circuitry or the sample and hold circuitry built in. Others require you to sample and hold externally. So pay attention, not all are equal, but you're looking for where the sample and hold takes place and the nature of the hold. The next thing that we're going to talk about, is we're going to talk about low pass filters. Again, if you have heard of low pass filters before in signals, give me a thumbs up. If you never heard of them before, give me a thumbs down. I'm not going to believe you if you tell me you never heard of them, because I'm sure you did simple RC low pass filters.
Yeah, they should have heard the term, but actual discussions on filters and so on, we haven't done. That's a little bit later on in this course. We'll actually talk about the circuitry that does it. And in the signals and systems, we'll talk a little about the mechanism behind filtering from the transform side.
Oh, great. Okay, good. So this is to come. You can look forward to it. And Ryan has given me some feedback in the chat here saying it was in the BJT design project. You needed a filter for the BJT? Okay, so Fazil, we could note that apparently they needed to use a low-pass filter in the BJT design.
Okay, I'll check that. That would have been last semester. Okay, no problem.
Yeah. Okay, so I'm not getting involved in what the circuitry is. I deliberately did not put a circuit on here because I wasn't sure how far y'all had gotten with filters. But basically, you will get some filter design techniques, and that will depend on the characteristics that you want for the filter. But what I want to talk about is the purpose of the filter. So if we convert in a signal from analog to digital, then one of the challenges we have is that sampling we were talking about in the sample and hold is going to constrain the frequency of signals that we can detect digitally. That sampling rate is going to constrain the frequency of signals that we can detect. I believe you should have heard of the Nyquist. It's not the Nyquist criterion. I think it's the Nyquist criterion. Faisal, I have that right?
Yes, it is.
Where
I don't know if they would have heard
of it. Okay, good. So there's something called the Nyquist criterion, which boil it right down, it means that you can't detect frequencies whose frequency is higher than your sampling frequency, which seems a little self-evident. So if I'm sampling at a particular frequency, I can't detect frequencies higher than that. In fact, I can't reliably detect frequencies that are more than half the sampling frequency. So normally people will say, okay, if you're going to sample, you should be sampling at a rate that is at least 10 times the frequency you want to detect, which is great. The problem is that high frequency signals can sometimes look like low frequency signals, and that phenomena is called aliasing. So if you look at this diagram to the left, notice the dots. The dots represent the points at which we're sampling. The dots represent the points at which we are sampling the black oscillating signal. And you will notice that even though the black signal is oscillating very quickly, the sampled signal looks as though it is oscillating slowly. If you see that the sampled signal looks as though it's oscillating slowly, give me a scared face. If you see that the oscillating signal looks as though it's oscillating slowly, give me a scared face. So the red line is the signal we will think we see, even though the black signal is what is actually taking place. This phenomenon is called aliasing. So any high frequency signal will look like an aliased signal if it's sampled with a sampling rate that's wider than itself. So to get rid of this problem, what we have to do is we have to low pass filter the signal before the sample and hold. So by low pass filtering before the sample and hold, we get rid of those high frequency signals, and then we don't have to worry about aliasing in our sampling. So very often in signal conversion, you'll see a low pass filter, and then you'll see a sample and hold. And the reason for that is because in analog to digital conversion, you need to get rid of the high frequencies so that you don't have a problem with aliasing once you digitize the signal. For digital to analog conversions, you very often come across some low pass filters on the other end. And here we might be smoothing out the steps that are caused by the zero or the hold. So on the output, I'm converting from digital to analog. The digital signals only come every now and again, so I have to hold them. And as I'm holding them, they'll come out in steps. Maybe I want a smooth signal. I don't want coming out with these steps. I could use a low pass filter to help me smooth out the steps. So low pass filters are circuits that you're going to come across when you have issues connecting a digital signal to an analog, converting, a digital signal to an analog signal or vice versa. Okay. Now the actual business of the conversion, is sometimes a little counterintuitive. What we actually doing is we taking the value we sampled. We're taking the value that we sampled, and we're going to come up with a binary number that represents the voltage that we sampled. Now, in an ideal world, the dotted line on this graph would represent the conversion characteristic. In other words, I would like to get a binary code of 0 when my voltage is 0. And I want to get a binary code of 1111 when my voltage is full scale reference. So the dotted line on the graph, that dotted diagonal line, I'm not sure if you're seeing my mouse. The dotted diagonal line.
No, actually, we don't see the mouse as something that we notice with the with BBC. You're not seeing hands on mice and so on. I have to use a stylus to indicate all the time.
All the time, okay.
Yeah.
So the diagonal line, which I'm going to try to highlight here now, that line is the ideal characteristic we want for our conversion. If you see the diagonal for the ideal line, give me a thumbs up. If you see the diagonal for the ideal line, give me a thumbs up. Okay, now you're going to notice something about this diagonal line. The red staircase is the actual conversion characteristic for my E to D or my D to A. In other words, I'm going to get the code 0 only for some. Then I'll get the code 1 for some, 2 for some, 3 for some, etc. So I have a little staircase. What you'll notice is not all the steps on the staircase are the same size. Not all the steps on the staircase are the same size. So for this particular characteristic, the transition from 0 to 1 occurs about when the LSB gets set, it occurs at a fraction that is approximately, what is that, 0.25. So that's about 0.1. Now, this may or may not be ideal. The challenge we have is that we can only get 8 codes out of this ADC converter. We can only get 8 codes out of this ADC converter. So no matter how you do it, there's always going to be some error or difference between the ideal characteristic, which is my diagonal line, and the actual characteristic, which is my staircase. So anytime you're actually doing A to D or D to A conversion, there's an implicit error. There's an implicit error that you're going to get in performing this conversion. So often people will say to me, well, Miss, how do I get it to work out? Because in an ideal world, I want to divide up my signal. If it's 0 to 5 volts and I have a 2-bit A to D converter, I want to be able to have 0, 1, 2, 3, 4. So that 4 would be my full scale voltage and 0 would be my 0 voltage. But no, 0 is your 0 voltage and 3 is your full scale voltage. So it's never quite proportional. You always have to worry about if the steps are even and where the step transitions occur. And depending on the A to D converter or D to A converter that you're looking at, the characteristic will be slightly different as to where those steps are. So you need to pay attention. You might not get the code that you expect. You might not get the code that you expect. Does anybody have any questions about the fact that the staircase conversion characteristic is not the ideal straight line that we want? Okay. All right, so then we could talk about how we actually make a digital to analog converter or an analog to digital converter. So I'm going to start with the digital to analog first, and then we'll talk about analog to digital next. So simple example of how we could do a digital to analog converter is we could use what we call a R2R ladder. R2R ladder. And it's called an R2R ladder because the resistances in the circuit are of a resistance R and resistance 2R. If you see R and 2R in the circuit to the top left, then give me a happy face. If you see R and 2R in the circuit to the top left, give me a happy face. Waiting, waiting on 20. Now I'm presuming that you've already done adders, etc. in op-amps in this course, Faisal?
They did others in first year.
In first year,
10,
great.
11. Yeah.
So what we could see is that based on the position of these switches, we will get different currents going into the op-amp. And so the voltage out will be proportional to whether or not we connect VREF or ground to each of the bits. Yes? So an R2R ladder, and you could build this yourself using resistors and an op-amp. R2R ladder, you could take a 4-bit code from these switches and generate an output voltage. And if you didn't want to use switches, you could connect these 4 bits to some digital circuitry and it would generate an output voltage. Another technique that we typically use for digital to analog conversion is we use pulse width modulation. If you look at the diagram at the bottom right, you'll notice that in each period, the amount of time the signal is on changes. You'll notice that in each period, the amount of time that the signal is on changes. We refer to this as pulse width modulation. In other words, the amount of on time varies. Sometimes that's expressed as a duty cycle. So we express the on time as a percentage of the period. Or sometimes we just say an on time and an off time. So the initial period to the left-hand side of this drawing, the initial period on the left-hand side of this drawing is a 50% duty cycle. And the reason it's a 50% duty cycle is because we're on half of the time. Does everybody see that? If you see that on the left-hand side, what we have here is a 50% duty cycle, then give me a thumbs up. I've just circled in red. You have is a 50% duty cycle. You'll notice it's on for the same amount of time that it's off. We refer to that as a 50% duty cycle. The reason this is often used as a form of digital to analog conversion is because if you then take this pulse width modulated signal and run it through a filter, you will get a signal that averages an average voltage level that averages and varies according to the on time. So this signal is clearly a pulse width modulated signal, but the average voltage you get is approximately linear, not quite. We could have a conversation about that. So very often, this is used as a rudimentary form of digital to analog conversion, especially if you're driving something like a motor or some other sort of inductive load. Okay. So the reason I wanted to talk about digital to analog converters first is because they are easier to build. We're going to talk about analog to digital converters now. So one way of doing analog to digital converters is to use a bunch of comparators. So you see your op amps here again. This time they configured as comparators. So you're comparing the signal to a reference signal, and the reference signal is generated by a resistor ladder. So you put the reference voltage at the top of a resistor ladder with resistors all of the same value. So what that means is you're going to be able to tap off. Reference voltages at appropriate levels. Now it's up to you, depending on how you build it, if you use a priority encoder or if you use different resistances to give you reference levels that are half of each voltage. And the idea here is that you take the analog voltage and you check it against each of these reference voltages. That'll give you a binary code. It won't be the binary output number yet, but it'll give you a binary code to tell you which of these levels it's greater than and which it isn't. And then you would use a digital circuit made up of some gates to transform that into the corresponding binary value. So flash converters, which is where we use a set of comparators, they have the advantage that you can build them and they're quick to operate. In other words, once the analog input voltage is there, we're just talking about the time for the signal to propagate through the comparators and through the digital encoder to get your output. So it's all about propagation time. Once the input changes, the constraint on this is the propagation time through the circuit. Even though they're fast, you could tell that they're going to require a lot of components, because if I wanted a 64-bit flash converter, I would need a lot of comparators, right? If I wanted a 64-bit flash converter, I would need a lot of comparators. So typically what you tend to find in most applications is we tend to use a successive approximation converter, which is a system on the right. Now this is a clocked circuit. So this would be the kind of circuit that you're building right now in your FPGA. So it's going to be a clocked circuit. You'll notice the clock signal on the right hand side here. Everybody see that clock signal? If you see the clock signal, give me a scared face. It's a clocked circuit. There's a clock signal on the right-hand side. If you see the clock signal, give me a scared face. So what actually happens in this case is that there's only one comparator. There's only one comparator. And I have my analog input voltage coming into this comparator. What is going to change is the voltage I'm comparing it to. So we start out by comparing it to a voltage that is halfway between my reference voltages. And we do that by setting the most significant bit and then running that binary signal through a digital to analog converter. So the way a successive approximation converter works is it makes use of a digital to analog converter. And we use that digital to analog converter to generate a signal matching the binary code. And we use the comparator to tell us who's bigger. Based on the output of the comparator, we will either fix or change the most significant bit, and then we move on to the next most significant bit. So for those of you who remember from programming, do you remember when you do a binary search, you start in the middle, and then you either go halfway up or halfway down, and then you jump quarter way on the next step? If you remember a binary search, then give me a thumbs up. If you remember a binary search, give me a thumbs up. A success approximation converter works on the same principle. We start with the most significant bit and we decide, okay, is that 0 or 1? And then we move to the next most significant bit. Now, the number of times I have to go around this circuit depends on the number of bits I have for my conversion. So if it's an 8-bit converter, I'm going to have to go around here 8 times. If it's a 64-bit converter, I'm going to have to go around 64 times. So the advantage of a successive approximation converter is that it needs less parts. The disadvantage is it needs more time because I'm going to have to cycle around as many times as I have bits. All right, so the last thing we said is that sometimes we want to transmit analog signals using a digital code format because noise is everywhere and we want to make sure our signal does not get corrupted. And you can see why. If we look at the diagram at the bottom left, if you look at the diagram on the bottom left, even though there's noise corrupting my ones and zeros, we could see, we could still kind of recover, okay, that's probably a 1, that's probably a 0, and that's probably a 1. Yes? So even though the noise affects us, the fact that we have some hysteresis encoded in the fact that we have an indeterminate region, that kind of protects us from noise. So digital signals tend to be robust in the face of noise. Not only that, we can also add additional bits to the signal for error detection and correction. So parity would be an example of that. So you'll see on the flow chart here for even parity, yes. Imagine we want to transmit the signal 1011. We would count the number of ones. In this case, there are 3 ones. And then we add a 1 to the parity generator. The idea is that with even parity, the sequence of bits we send will always have an even number of ones. So I had 3 ones. I'm going to add an extra 1 to make it even. So the data I actually send is not 4 bits, but 5, where that last bit is set to a 1. So the good news is that I can add an extra bit to help me figure out if something went wrong. The good news is I can add an extra bit to help me figure out if something went wrong. The bad news is I need to send an extra bit. So when the signal arrives at the receiver knows it's doing even parity and it can check the number of ones. If it receives a signal that has an odd number of ones, then something is wrong. So it could discard that signal and ask for a retransmission. So this is the parity bits is the very simplest means of error detection. It can't even correct. There are much more sophisticated codes. But that is the principle. Sometimes we want to transmit an analog signal a long distance or in the face of a lot of noise. And in that case, sometimes it's in your interest to code it as a digital signal and maybe add on some extra bits to help you. All right, so to wrap up today, the reasons why we want to talk about digital and analog together in one space. First is because under the hood, digital is analog, and we need to check to make sure we're not breaking anything. Check voltage limits and current requirements. Second reason is because sometimes we want to use digital methods to process analog signals, and that involves a conversion. If we're going to do that, you're probably going to need to do some signal conditioning. We looked at two basic things, a low pass filter and a zero order hold. We want to remember that that conversion characteristic is not ideal and it's going to introduce some error in converting in or out. And you want to remember that the technology choice you make for your digital to analog converter or your analog to digital converter matters because they take different amounts of time, just the principle of operation, and they require different amounts of circuitry, which would require different amounts of power. So the technology choice for D to A and A to D matters. You want to remember that analog signals are prone to noise, so sometimes we want to convert them to digital just to get them to transmit further. And we can detect and correct using additional bits. And last but not least, I'm going to blow your mind now. We only talked about voltage signals here today. You could, in fact, have been talking about signals that are current signals. In fact, 4 to 20 milliamp current loops are an industrial signal transmission standard. Not so much these days again, but it's still out there on a lot of plant floors. So the signal you may be considering is not necessarily a voltage signal. But for the purposes of this discussion, we confined it to voltage signals. So that is it for today. My apologies. I think I went over by 2 minutes.
No, not an issue.
I hope that was helpful and interesting. Anything that anybody wants to ask? And if not, my reflection question for today is, did you learn anything new? What was the most surprising thing you learned today? Just drop that for me in the chat as you're leaving.
All right, so some of the stuff they would have met already in a slightly different form between here and the signals and systems class. We did mention the fact that analog signals are not necessarily only voltage, but we spoke about, analog and real world signals are not necessarily only voltage, but currents and pressures and temperatures and all those kind of things as well. So we did mention that and how we would interface those things into electronic systems and process them as well. So this was a nice bridge in that regard, and hopefully they'll remember. But some of this stuff we haven't met as yet, but hopefully they'll remember it as we go along, and I'll try to refresh their minds as well.
Well, thank you very much for the opportunity to talk to you all today.
All right, so any questions, anyone, before we wrap up? And of course, you can always drop some questions online if you need some clarification, and we could get it to you as well. Yeah, get the answers. All right, well, if that's the case, I will stop the recording now. And